Electrochemistry is the use of oxidation reduction or redox chemistry to look at electricity and looking at the electrons moving from one component to another. There are a number of different uses of electrochemistry. There can be things like electroplating, where you input electricity to force one metal to precipitate on top of another. That's the basis for chrome plating on cars and other things, to get chrome to adhere to steel. Another use is through electrolysis, that is, in having electricity be input into a system to break it apart, to break that compound into its original components. An example of that would be the electrolysis of water. Water itself is H2O, comprised of hydrogens and oxygens. And if you input the correct amount of electricity, you can break that H2O molecule apart into either hydrogen gas and hydroxide, or oxygen gas and acid molecule, or acid ion. Probably the most common use of electrochemistry is the use of batteries, chemical batteries. And these are chemical reactions that are occurring in these small batteries that transfers electrons from one redox component to another. And that flow of electrons is flowing from one side to another, from the positive end to the negative end. And when you place a battery inside a device, you're completing that circuit. When you complete that circuit, the electrons are then able to move through the device, through the wire, from one side of the battery into the other, and complete the electrochemical reaction. In this experiment, you're going to be looking at a few different redox reactions. You're looking at comparing oxidation and reduction strengths, as well as the components of batteries, looking at how a battery is set up, the different structure of it, the flow of electrons, where do they go, the different components of the battery. You're also going to be using simulations to measure the electricity or the voltage that's generated through different chemical reactions, both in standard conditions and in non-standard conditions using the Nernst Equation. So as you work through this experiment, you're working through this simulation, you should get a better understanding of electrochemistry and of specifically galvanic chemical cells.
In the previous experiment, we went through oxidation reduction reactions, or redox chemistry, which involves electrons being transferred completely from one compound to another. In that experiment, we looked at balancing these equations. We were looking at this chemistry from the viewpoint of the atoms and the ions themselves. In electrochemistry, we're looking at it through the viewpoint of the electrons. The electrons are moving from one spot to another, and in that movement, they're generating a voltage potential. They're generating electricity through the chemistry. So as a quick recap of last time, the terms oxidation and reduction. So oxidation is the process where an electron is lost, and reduction is the gain of electrons. They're a little bit counterintuitive. But in an electrochemical cell, there are two separate areas, and these are termed the cathode and the anode. The anode is the particular spot in an electrochemical cell or a chemical battery where oxidation occurs. Electrons are leaving the anode. On the cathode, this is the site of reduction. Electrons are coming to the cathode. And since electrons are leaving the anode and flowing to the cathode, this is the flow of electrons. They're flowing from the anode to the cathode. Now, we looked at varying half reactions before, where we're looking at just either the oxidation half of the reaction or the reduction half of the reaction. And in the simple example here of a simple redox reaction, we have zinc metal, solid zinc, reacting with copper ion to form zinc ion and solid copper. So the half reaction, electrons are leaving the zinc. It's going from zinc metal to zinc 2+, and electrons are being gained by the copper ion. It's going from copper ion to copper metal. And in these half reactions, there is that flow of electrons. Another term that was gone over a bit in the previous experiment was oxidizing and reducing agents. And in this experiment, the first part of this experiment is focusing on these half reactions of simple redox reactions and looking at ranking the oxidizing and reducing agent strengths. And that can be done through an array of different reactions. So in the experiment, there's going to be a setup similar to this, where you're going to be reacting different metals, and the metals themselves are reducing agents, and reacting those with different salt solutions, metal ions. And the metal ions are the oxidizing agents. The reducing agents lose their electrons and become an oxidizing agent. So when you mix these things together, you can rank their strength by order of how many times they react. How reactive are they? In this case, this example here, there's sodium, calcium, and aluminum. And these are all reducing agents. The sodium undergoes 2 reactions. The calcium undergoes 1 reaction, and the aluminum does not react with anything. So the overall ranking or the strength of these reducing agents is that the sodium is stronger than the calcium, and that is stronger than the aluminum. The opposite ranking is also true when you're looking at the oxidizing agent strengths. What was a very strong reducing agent, the sodium metal, is now a weak oxidizing agent as the sodium ion. And the weaker reducing agent, the aluminum metal, is now the stronger oxidizing agent of the aluminum ion. So in this kind of the first part of the experiment, we're going to be looking at different redox reactions, balancing of these simple redox reactions. Nothing as complicated as the balancing in acidic or basic conditions as the last experiment, but just balancing simple redox reactions between metals and their ions, and ranking their relative strengths. This would be the first part in determining which ones would be utilized in an overall redox reaction and generate an electrical potential in electrochemistry. Now, I had mentioned a bit ago about the terms cathode and anode, and these are the different poles on a battery, or what could be termed an electrochemical cell or a galvanic cell. On a battery itself, on a regular battery, this would just be the positive and the negative ends of the battery. So in a chemistry lab or in a chemical setting, a galvanic cell is something just like this, where you have two pieces of metal or two places where electrons can come from, the cathode and the anode, and these are in solutions. One of them would be separated out by some other form of a barrier. And in this diagram, it's through kind of a porous container. And in the simulation, that they're in separate wells or separate beakers, but they can be connected by what's termed a salt bridge. And that is just so they're all fully connected through solution, so that way the electrons can move around and that the circuit can be complete. So in the anode, this is where oxidation occurs. So in our simple setup of zinc and copper, the anode, this piece right here, would be made of pure zinc, and the solution that it's sitting in would be a solution of zinc ions. So zinc chloride, zinc sulfate, zinc nitrate, something like that. And it will be connected with a wire. And through this wire, the electrons are moving through the wire and into the cathode. And the cathode itself is sitting in the solution of the cathode salt. So in this case, the cathode would be a piece of copper sitting in a solution of copper 2+. So again, copper chloride, copper sulfate, something like that. And over time, what you can see is the reaction happening without the two even touching. So if you were to take a piece of zinc and put it in a copper solution, what you will see over time is that the zinc might turn a little black, and then all of a sudden it's kind of like this bronzy copperish color. The copper comes out of the solution. It's going from copper 2+ to copper solid, and it plates itself on the zinc. This is the basis for electroplating of one metal on top of another. And the zinc itself is slowly dissolving. It's going from zinc metal into zinc ion. Typically, that would happen when you mix those two together. It's a very well-defined redox reaction. It happens fairly quickly, where you'll see the zinc metal reacting with copper 2+ to form zinc 2+ and copper metal. But in an electrochemical cell, they're completely separated, but they still, the reaction still occurs. So when it happens like this, over time, this anode would slowly dissolve. This zinc anode would slowly dissolve into zinc ion as it's losing more and more electrons through this wire. And the cathode would grow larger as it's a piece of copper sitting in a copper solution. These copper ions are gaining these electrons that are coming in and connects itself back to the cathode, and it grows itself into a larger piece. And what's termed the salt bridge or through this barrier, that's where the ions themselves can kind of move through just so it's all balanced. This particular salt bridge or solution or this porous membrane, it doesn't really allow the ions themselves to pass through it, but the electrons can move through. So that way it's a continual circuit and it's a closed circuit, so that way it can continue on reacting with undergoing the chemistry through an electrical process. In electrochemistry, you'll also see a chemical reaction written in this way, where you have the metal and metal ion of the two components, and there's these vertical lines. Everything is written in the same way. The anode is always on the left-hand side, separated by two lines, with the cathode on the right-hand side. And the pairings are separated just by one line. And this, simple enough, the zinc, I like to read these just like reading a book or something like that. You're reading from left to right. The zinc is turning into zinc ion, while the copper ion is turning into copper metal. And that is the overall electrochemical reaction that would be happening between these two components. I had mentioned different batteries, and while what I just showed through the galvanic cell was more of a simpler setup, this is the chemistry of an alkaline battery, just a Duracell Energizer, a battery that you would buy at home, where this is under basic conditions. It's an alkaline battery. So it is zinc and manganese dioxide. And if you were to ever slice open a battery, what you will find is in the middle is a bunch of zinc powder, and that's in a hydroxide solution. So that is the anode. Electrons are coming from this. The zinc is going to zinc oxide. The electrons pass through a post in the middle, many times carbon, and passing through the device that it's trying to power. So this is the negative end of the battery. The electrons are going through the device or whatever you're powering with the battery, coming into the positive end, and this positive end is in contact with a powder of manganese dioxide, again, in a slurry of hydroxide solution. And the manganese dioxide undergoes a reduction to this manganese oxide form. So when you're putting a battery into something, the electrons are moving from the zinc through your device and then ending up in this manganese dioxide black powder. And as those electrons are moving through your device, it's generating a chemical potential. It's generating a voltage. That movement of electrons is what generates electricity. And if you were to measure the voltage of a battery, it's a little under 1.5 volts. And that's because of this chemistry reaction. The overall voltage of an alkaline battery, and this is the same for a AA, a AAA, a D, is 1.43 volts, because the reduction of manganese dioxide is enough to generate 0.15 volts, and the oxidation of zinc is enough to generate 1.28 volts. So combined, they generate 1.43 volts of electricity from this chemical reaction.
The reaction of zinc metal and copper ion is a fairly straightforward redox reaction. A piece of zinc metal can be placed in a copper ion solution, in this case copper sulfate, and you can very quickly see that the zinc metal is coated with a black material. This black material is a coating of powdered copper. In a galvanic chemical cell, this reaction occurs without the two substances coming in contact with each other. In a galvanic cell, a solution with its appropriate metal is placed in two separate containers. On the left is a solution of copper sulfate with a piece of copper metal. On the right, in a porcelain cup, is a solution of zinc sulfate with a piece of zinc metal. The porous porcelain cup is placed inside the copper sulfate solution. The porcelain cup is porous enough to allow for electrons to pass through. The voltmeter can then be attached to both the copper electrode and the zinc electrode. In doing so, the voltage reading of this reaction is seen to be 1.06 volts. The standard potential for this reaction is 1.10 volts. However, under these conditions in the lab, it is not perfectly standard conditions, and the Nernst equation could be used to calculate this value without a measurement. In this reaction setup, the zinc piece is the anode, and oxidation takes place at the anode of an electrochemical cell. Over time, the zinc will slowly dissolve, and the solution of zinc sulfate will get more concentrated. On the reverse of that, the copper electrode is the cathode. Reduction occurs at the cathode, and over time, the copper ion in solution will reduce and plate itself onto the copper metal. So over time, the concentration of copper ion will decrease.
So as was just shown, you can measure the chemical potential voltages of a chemical reaction. If you can hook up something between the two components, between the anode and the cathode, you can measure the flow of those electrons and the voltage that it generates. But you can also calculate the voltage of a redox reaction just based on standard potentials. Typically, the standard potentials are written in either in tables on textbooks or online as reduction potentials. So in our case right here with the zinc and the copper, the reduction reaction of Copper would be copper 2 plus, gaining 2 electrons to form copper metal, and that has a potential of 0.34 volts. The reduction of zinc from zinc ion gaining 2 electrons to go to zinc metal has a voltage of negative 0.76 volts. Those are the standards that would be given in reduction potential tables, either in textbooks or online. But what if you want to know the reduction or the potential of the oxidation half reaction? So in this case, the copper 2 plus is going to copper 0, solid copper. So this is the potential, 0.34 volts. But the zinc is going to zinc ion. It's being oxidized. So instead of the electrons flowing this way, or instead of the zinc gaining electrons, it's losing electrons. And all that does is it reverses the direction of the voltage. So in the case of copper, it was for the reduction, it was positive 0.34 volts. The oxidation would be negative 0.34 volts. The reduction of zinc, zinc ion going to zinc metal, is negative 0.76 volts. So the oxidation of zinc turning into zinc ion would be positive 0.76 volts. And these tables of varying standard potentials, again, typically only the reduction potentials, because you can always determine what the oxidation potential is. These are textbooks online in various places. So to calculate a chemical potential for the entire reaction, looking at zinc metal plus copper ion going to zinc ion plus copper metal, you can do that based on just the reduction potentials. And the calculation for that is cathode minus anode. So at the cathode, reduction occurs. And so that's 0.34 volts. The copper is being reduced from copper 2 plus to copper metal at the cathode. The anode is where oxidation occurs. And the reduction potential of the zinc reduction reaction is negative 0.76 volts. So it's cathode minus anode. So it's 0.34 volts minus a negative 0.76 volts to give an overall potential, an overall voltage of this reaction as 1.1 volts. You could create a battery just like a regular household battery using this chemistry, the chemistry of zinc and copper, but it wouldn't be as powerful. It would only generate 1.1 volts of electricity versus the 1.43 that the zinc and manganese dioxide would produce. There are a number of different chemical batteries based on different types of chemistry. There's the lead acid battery, there's nickel cadmium batteries, there are lithium ion batteries, and they all go through the same type of chemistry. They all go through oxidation reduction, and by looking at the exact chemistry and the standard potentials, each combination, each different battery combination will provide a different level of voltage. Another thing you can do with these batteries, and this is more in physics or like electrical, is you can tie them all together. While one cell of this battery. And it doesn't matter if you have more or less of the material. The chemistry itself generates 1.1 volts. But if you take two of these cells and tie them together, combined, it would generate 2.2 volts. They add together. And that's how a 9-volt battery has that much voltage. It's 6 of the smaller galvanic cells all packed into that one battery, and that generates 9 volts. Now, this type of simple calculation, just looking at the two different voltages of the two half reactions and then adding them up, or cathode minus anode, that can give you the standard voltage under standard conditions. However, chemical reactions don't always occur under the same conditions. And this is where an equation called the Nernst equation comes in. This gives what the actual voltage would be under non-standard conditions. So with standard conditions, the temperature is constant. It's exactly 1 molar solutions, but many times the temperature is not constant, and you can have concentrations of a wide range of different solutions. And the Nernst equation takes all that into account. So the Nernst equation is shown here, where you have the standard chemical potential, this E0, that is the potential that would be calculated from the standard reduction potentials, just like in these calculations. And then it's taking into account the temperature and the concentrations of the two different components. So the Nernst equation is E0, the standard potential, minus the gas constant times the temperature in Kelvin, divided by the number of electrons being transferred in the redox reaction. So depending on the reaction itself, this will vary, times Faraday's constant, which is 96,500, times the natural log of the oxidation analyte divided by the reduction analyte. And what these two terms are is the top number, that oxidation analyte, that is the concentration of what's being generated by the oxidation half reaction. So in this reaction, you have the oxidation of zinc going to zinc 2+. So the oxidation analyte is the concentration of zinc 2+. The reduction analyte is the chemical that's being consumed by the reaction. What is lowering in concentration over time? And this is the concentration of the electrolyte at the cathode. So in this reaction, you have the copper 2+ slowly turning into copper solid. This concentration is going down over time. And so these initial concentrations are what go into the Nernst equation. An example of the Nernst equation could be given with our setup like this. So we have our galvanic cell, we have our battery, zinc and copper. But this is at 37 degrees, and the copper 2+ solution is at a concentration of 0.125, and the concentration of zinc solution is at is 0.411. So what is the overall potential? What is the overall voltage of this reaction under these specific conditions? So first, you see what is the standard potential. You do cathode minus anode, and for this, we have a standard voltage of 1.10 volts. Temperature should be in Kelvin. It's given here as 37, so plus 273 to give a temperature of 310 Kelvin. In the balanced equation and the balanced full redox reaction, there are 2 electrons being transferred, and R and F are constants. So we can plug all of these components into the equation, and we're left with just solving for or figuring out what the oxidation analyte is and what the reduction analyte is. So in the full chemical reaction, zinc ion is being generated, and that's what goes on top into this oxidation analyte. And our concentration is 0.411 molar. On the other side, in the reduction, copper 2+ is being reduced. That's slowly going down. And at this low concentration, with this copper 2+ going down, that's the reduction analyte. And now you have all of the components of the Nernst equation to plug these in. And what you find out is that under these specific conditions, the voltage is lower. It's not quite the same. The voltage went down by a small amount, but still, it's only 1.10 volts to begin with. And it went down by 0.05. So you can use this equation, you can use this Nernst equation to figure out what is the chemical potential, what is the voltage of these redox reactions under a wide variety of different environments. In lab, this experiment focuses on a number of different electrochemical cells that you are going to prepare and measure the chemical potential. In the lab, you'll prepare these galvanic cells or these chemical batteries using a small beaker and a porcelain cup. This porcelain cup is unglazed and acts as the salt bridge in these experiments. So when you prepare the galvanic cell, you'll be taking the individual electrolyte solutions and adding one of the electrolyte solutions to the beaker with its appropriate electrode. In this case, the blue copper sulfate solution is in the beaker with the brown or copper piece of copper electrode. The other electrolyte solution is placed in the unglazed porcelain cup along with the electrode itself. In this example, it's the zinc electrode. There is zinc sulfate solution in the cup and a zinc electrode. You'll prepare these separately. So a beaker with the liquid and the porcelain cup on the side of that with the liquid as well. You can then attach the different leads from the voltmeter. Red should be going to the electrode where reduction is taking place, and black should go to the electrode where oxidation is taking place. You can connect these leads to the separate electrodes and then pick up the entire porcelain cup, place that into the beaker, and record what is the voltage of that electrochemical cell. When you are preparing these galvanic cells, the metal electrodes are reused, so that means they can corrode and oxidize over time and build up a slight layer of their oxides on the outside. To make sure these are clean and have good contact with everything, there will be pieces of sandpaper in the room that can be used to kind of rub off any oxide layers and clean up the different metal electrodes, or a slight dilute acid solution. The other thing that I'd like to point out is the electrode or the voltage reading should always be a positive voltage. If it ends up being a negative voltage, this means that the wires are connected to the wrong side. This voltage reading is directional. This is telling, or this is indicating what the flow of direction, what the flow of electrons is. So if there is a negative reading, you can just detach these two leads and switch them around, and that should give you the positive voltage reading.
Much of this experiment involves the preparation of galvanic cells and measuring their voltages using a voltmeter. The range on the voltmeter should be set to 20 volts. The type of current or voltage that is being used is direct current, DC, just like a regular battery. On the varying types of voltmeters, the DC symbol is the letter V for voltage with a solid and dashed line above it. The leads on the voltmeter are black and red. The black lead, which is connected to what is called the COM port on the voltmeter, is a negatively charged lead, and this is to be connected to the anode. The red lead, also referred to as the positive lead, is connected to the cathode. You will be preparing multiple different galvanic cells using a wide variety of different electrode materials. The electrodes themselves consist of a piece of metal as well as that metal ion. For example, the copper electrode consists of a piece of copper metal and a solution of copper ion. To prepare these galvanic cells, you will take one solution and place about 20 to 30 milliliters in a small beaker, and to this solution add the metal electrode. Inside an unglazed porcelain cup, you will place the second electrode. The solution, about 10 to 15 milliliters, is poured into the porcelain cup, and the accompanying piece of metal is placed inside. The two leads should be connected to the pieces of metal before completing the circuit. In this example, I have copper and the copper solution in the beaker, and the zinc and zinc solution in the porcelain cup. The copper solution, or the copper electrode, will undergo oxidation, and therefore I will connect the red lead to the copper. The zinc will undergo reduction, and therefore I will connect the black lead to the zinc. Once the two leads are connected, you can then pick up the porcelain cup and place it in the beaker solution. The resulting voltage can then be read as 1.15 volts. You can then record this voltage to determine that the electrochemical reaction between copper and zinc has a chemical potential of 1.15 volts in this measured experiment.
The first part of the experiment is preparing different galvanic cells of these 4 different electrodes. You will have solutions and metal electrodes of iron, magnesium, zinc, and copper. And you will prepare every combination and measure the chemical potential. So there will be a total of 6 different combinations. And while the directions may say a specific solution or electrode goes in the beaker versus the cup, it really doesn't matter exactly. What matters is how you attach these different leads. The red lead should be attached to the site where reduction is taking place, where the electrode where reduction is taking place. And the black lead should be attached to the electrode where oxidation takes place. The black lead on a voltmeter should be connected to the anode, while the red is connected to the cathode. And like mentioned, if there is a negative voltage when you read these, you can just switch the wires around and that should give you the positive voltage of that. So when you're preparing these, there will be these 4 different metals. The iron electrode is just an iron nail. The magnesium electrode is this small, thin ribbon of magnesium. The zinc electrode is a pale gray material, and the copper electrode is the copper colored piece of metal. So you'll then record the voltages of these 6 solutions, or these 6 galvanic cells, and compare that to what the theoretical voltage is. All 4 of these electrodes have known standard reduction potentials, so you can use them to determine what is the theoretical chemical potential for this reaction and what is your percent error associated with that theoretical value based on your measured voltage.
In the first part of the experiment, you will be preparing a number of different galvanic cells which have different combinations of electrodes, and you'll be measuring their chemical potential and comparing that to the calculated chemical potential using their standard reduction potentials. The different electrodes are iron with iron 2+, magnesium with magnesium 2+, zinc with zinc 2+, and copper with copper 2+. You will be preparing a galvanic cell in all combinations and measuring their different voltages.
The next part of the experiment is identifying an unknown electrode. So in the lab, you're given a piece of metal. It's of an unknown material, and it's electrolyte solution. What you're going to be doing is just preparing 1 galvanic cell with a known electrode. That's one of the 4 from part A, either copper, iron, zinc, or magnesium. And in either the cup or the beaker, again, it really doesn't matter. So you'll be placing that in the known electrode on one and the unknown metal electrode with its solution in the other, connecting these together and then measuring the voltage. Since the known electrode does have a known standard reduction potential, and you're measuring the actual voltage of this combination, you could determine what the other standard reduction potential is for this unknown electrode. Once you have that unknown standard reduction potential, you can compare that to the list, the given list of standard reduction potentials, and try to identify what is this electrode.
In the second part of the experiment, you'll be determining the standard reduction potential of an unknown metal. To do this, you'll prepare a galvanic cell using one known electrode and the unknown. Just as in the first part, you will have a beaker containing the electrode solution and the piece of known material. To the porcelain cup, you can then add 10 to 15 milliliters of the unknown electrode solution and the unknown electrode. You can then attach the black and red leads and complete the circuit by placing the porcelain cup in the beaker. Using the measured potential and the known potential of, in this case, the copper, you'll be able to determine what is the chemical potential or the standard reduction potential of the unknown electrode. You can then compare that to a list and determine the identity of the metal and metal ion solution.
The third part of the experiment looks at what's called the concentration cell. So in this part of the reaction, you're using copper sulfate and a copper electrode in both the beaker and the porous cup. And while normally, under normal conditions, there will be a zero voltage. Everything is the same on the inside and the outside on both sides of the salt bridge. However, what you're going to be doing in lab is adding sodium hydroxide to the beaker. And what that does is precipitates out some of those copper ions with the hydroxide in the form of solid copper hydroxide. Now, the concentration in the beaker is lower than the concentration inside the porcelain cup. And this difference creates a chemical potential. It creates a voltage. So you can see that in the reduction reaction, copper 2+ is going to go to copper metal. And in the oxidation reaction, copper metal would go to copper 2+. All of these reactions want to be in balance with each other, and especially in terms of concentration. So when these two concentrations on the inside and outside of this beaker are unbalanced, they want to go back and reach that balance between them. So that means the solution in the beaker, which is low, will want to increase its concentration of copper ion. So that would be the copper metal being oxidized into copper ion. So that's this top part of the Nernst equation, the oxidation analyte. Inside the beaker, that concentration is higher than, or inside the cup, that concentration is higher than what's inside the beaker. So in theory, it would want to be lowered to maintain that equilibrium, to make sure that eventually the concentrations are the same. So that starting concentration will want to go down and reduce to copper metal. That 0.1 molar solution would be this denominator in the Nernst equation, this reduction analyte. So when you measure this chemical potential, you'll have, in theory, the standard potential for that reaction should be 0. And R is the gas constant. You'll measure the temperature. There are 2 electrons being transferred back and forth for in the Nernst equation. F is Faraday's constant. And since the reduction analyte will be that initial concentration inside the porcelain cup, the 0.1 molar, you can then go through this and calculate what is the concentration of the copper ion in this beaker. So with this setup, and really for any of these, once you have a voltage reading, you can also use that to determine some of the thermodynamics. The Gibbs free energy of this equation, or of this chemical reaction, is equal to the negative N, or the number of electrons being transferred, times Faraday's constant, times the chemical potential of the cell. And with Gibbs free energy, you can then use that to determine the other chemical properties, or the other thermodynamic properties of enthalpy and entropy.
The third part of the experiment is again setting up a galvanic cell. However, in this case, you're going to be preparing the cell with the same electrode, and the voltage will be generated by only a change in their concentration. You'll be preparing a copper concentration cell by placing an amount of copper in the copper solution in the beaker, copper solution in the porcelain cup, and the copper electrode in both the cup and the beaker. You can see that when both of them are placed inside, there is no resulting voltage. However, if we lower the concentration of one side of the electrode by precipitating copper ion with sodium hydroxide, adding about 2 to 3 milliliters of 1 molar sodium hydroxide, this causes a precipitate of copper hydroxide to form. This precipitate is no longer available to transport anions and electrons. So when the cup is placed inside, there is now a voltage reading that is comparable to the concentration inside the beaker. You will be measuring the chemical potential of your setup and then determining what is the concentration of free-floating copper ion inside the beaker. You will be using the Nernst equation to determine this and measuring the temperature of the copper sulfate solution, and by recording that initially is 0.1, you can determine what is the concentration of copper ions in the beaker.
The last part of the experiment is similar to the concentration cell, where you're going to be playing around with the concentrations. However, where in the first one, in the concentration cell of the copper ion, you were calculating, you were using the Nernst equation and determining exactly what the voltage is and what the concentration is. This part of the experiment is a little bit more theoretical and conceptual. So you'll choose any one of the combinations from part A, any of those 6 chemical potential reactions and construct that cell one more time and measure the voltage. What you'll then do is take whichever material you have in the beaker and prepare a dilution of that. You can take 10 milliliters of the stock solution and 40 milliliters of water to create a much more dilute solution in the beaker. And then in the porcelain cup, it will remain the standard stock solution concentration of 0.1. So you'll measure initially where they are both the same concentration. You'll measure it where the beaker solution is at a lower concentration and the porous cup solution is still that 0.1 molar. And then you can switch them. The solution you have in the beaker will maintain that 0.1 molar concentration just from the start. And you'll prepare a dilute solution, which you would place in the porcelain or the porous cup. So when you're going through this, you're thinking about what is the oxidation reaction, the half reaction, what is the reduction half reaction. Over time, what would happen to these concentrations of electrolyte? Would the oxidation reaction, the electrolyte involved in that, would that be increasing or decreasing? Would the reduction electrode solution be increasing or decreasing in concentration over time? In the experiment, you're then looking at when you do lower these concentrations separately, what happens to the overall voltage? Does it increase, decrease, or stay the same? And using that information, you can determine what will happen to the voltage of a chemical oxidation reduction reaction over time as it progresses.
The last part of the experiment also involves preparing galvanic cells using varying concentrations. You will first prepare a galvanic cell of any of the combinations of the first part of the experiment. In this case, something like a copper and zinc galvanic cell. After which, you will prepare a dilute solution of one of them. The dilute solution could be approximately 10 milliliters of one solution and 40 milliliters of water to prepare a diluted solution of copper sulfate. You can then use the regular 0.1 molar solution of the opposite electrolyte and complete the circuit and measure what is the chemical potential under these conditions. You would perform 3 measurements. First, the measurement of the 0.1 molar solutions of each solution, and then 2 measurements using dilute solutions. One using a dilute solution in the beaker and the 0.1 molar solution in the porcelain cup. And in the next solution, you would prepare 10 milliliters of the other solution and 40 milliliters of distilled water and place that solution into the porcelain cup and the 0.1 molar solution in the beaker and measure that chemical potential. You're looking to see how these things would change as the concentration changes. What would be the voltage as the concentration of each individual electrolyte changes? And think about how these concentrations would change over time as the reaction would progress.